in the heart of Nanyang Technological University. Within the labs of CCDS, for 10 weeks, 8 researchers venture into unfamiliar territory, armed with laptops, code, and an unwavering determination to make things work. Their mission? To study and guide the behavior of a rare and curious creature, the marmot. In the natural world, the marmot is small and easily overlooked. Yet, in the digital world, it has achieved something far greater and rather unexpected. This moment of unexpected behavior has inspired the name of our creation. Much like its name, this marmot too can behave in ways that surprise us. And to study it, this expedition team is required. For a start, at the core of the marmot lies the Raspberry Pi. It binds the STM32 Android interface and algorithm into one harmonious whole. Yet in this multi-threaded workflow, overlapping instructions threaten to unravel order. The team then uses semaphores and locks to enforce a one command, one action's sacred rule, not to be the fastest, but for reliability. Next, to navigate its environment, the marmot must also learn to see. Using the YOLO Vive 11 architecture, the team trained across 500 epochs with deliberate variety to thwart overfitting. In the end, the marmot was able to achieve 99% detection on most symbols, though not without humbling misses that spurred refinement. Besides seeing, the marmot must also decide. At its core, an algorithm determines how it reacts. For each obstacle, it envisions 4 view states. Then, the A-star algorithm builds the cost matrix between each obstacle, measuring distance alongside turning, reversing, and obstacle perils. Then Kernighan heuristic solves the TSP, revealing near-optimal Hamiltonian paths. However, practicality prevails, as increasing permutations and iterations overwhelm the marmot. Yet thought alone cannot move the body. For that, the marmot relies on the STM32. Connected to the Raspberry Pi through a white USB, this microcontroller governs the essentials: motor pulses driving wheels, steering angles from the servo, and inertial awareness from the IMU. But flaws emerged in the wild. Rear wheels drifted unevenly off course. As turns demanded mastery, the team used trigonometry to shape the 3-point turn for grid-perfect reorientation. Each trial forged harmony, transforming thought to flawless action. But perhaps the most fascinating element is not within the marmot itself. It is the Android application, designed not just as a tool, but an expression of the journey itself. Upon awakening, the marmot echoes the researchers' frustrations. Through Bluetooth, the controller and creature are linked, and the arena opens. With a touch, obstacles appear, rotate, or vanish. When the command is given, a path is planned, and the marmot sets off, accompanied by a light-hearted music that turns testing frustrations into joyful experience. The Task 2 page introduces a ritual of release, where one must first release the beast before setting it in motion. In the end, one question lingers: is the marmot the machine, or the minds that guide it? What began as lines of code becomes something more. 8 individuals navigating obstacles of their own through failures, frustrations, sleepless nights, and moments of breakthrough, learning, adapting, responding. Just like the marmot itself, it sees and decides, and behind it, a team that has learned to do the same. Together, they are no longer separate parts, but one system moving forward.
love you so. Hey, that's what you'll say. You'll tell me, baby, baby, please don't.
Taking advantage of a multi-threaded workflow in conjunction with the various interfaces between the RPi, STM, Android, and Algo, the RPi serves as the brain that connects all the components together. Part of the challenge in this multi-threaded workflow is race condition. Therefore, we implemented an entire workflow that guarantees one command, one action by the algorithm to the RPi and to the STM and to the Android through the usage of semaphores and locks.
Generate 4 possible view states for each obstacle before iterating through permutations of all view states for all obstacles.
For each combination, we use A star algorithm to generate a heuristic estimate matrix from each view state to all other view states. This estimate considers not just distance, but also movement constraints like turning, reversing, and avoiding obstacles.
We then use the conjugate heuristic to solve our TSP to discover the most optimal Hamiltonian paths through our selection of view states.
As much as we wanted to increase the number of iterations to iterate through all permutations, it wasn't feasible as we added more and more obstacles.
For image recognition, we utilized the YOLO V11 architecture where we trained a model based on a huge dataset that was manually captured and annotated. To prevent overfitting, we introduced variety in the dataset and utilized a total of 500 approach. Our model was able to detect up to 99% of most images. Subsequently, we increased the dataset with symbols of various backgrounds to improve its confidence.
Action, push, 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 push.
Turn to I. Like you say push. How? You can count that.
Yeah, yeah, oh.
Okay, you can count that.
Oh, yeah, okay.
Push,
Good.
push.
3, 2, 1, action.
The STM32 board works as a real-time controller for our robot. It sits at the hardware level and interfaces with all the time-critical parts like photo PWM, servo steering, encoder counting, and IMU reading. As a microcontroller, it runs these controls with predictable timings for traversing target distance or turning at an angle accurately.
The communication between STM32 and RPi is through UART serial over USB. This allows data to be transmitted and received to the RPi's USB port as a virtual serial interface.
One challenge we faced was tuning the turns. For task 1, we needed to make it so that the robot moves precisely from grid to grid during turns. It's also beneficial for the algorithm if the turns are tighter. Therefore, we decided to implement a 3-point turn, and some trigonometry was used in order to calculate the values for the turn.
The Android app is designed with the Marmot team in mind. Now, as a way to express our frustration, upon opening the app, we will have the Marmot screaming sound. Then, you will be led to our Bluetooth page where users can make the app discoverable, scan devices, and connect to nearby device. Now, upon successful connection, so let's say we're going to connect to our MDP Group 3,
the Bluetooth device is connected successfully.
a notification will be shown and user can proceed to the arena for task 1 or to task 2. Now, for the task 1 page, the design is such that users can press anywhere in the grid to place the obstacles. Touching the obstacle again will rotate the obstacle. Now, if you want to remove the obstacle, all you just need to do is to drag your finger out of the grid. Once ready, users can send the obstacle data to the algorithm API for calculation. And once done, you can press start to move. A timer is included for ease of viewing and random music will be played to light up the move. Finally, for task 2, we have included a 2FA function where users have to release the beast before they can start the robot. Random music will also be played to light up the move. Overall, what makes our app unique is the Marmot team as well as having music to make the testing task fun and memorable.